Okay, let's dive into this. We're not just going to define Kubernetes with a bunch of textbook terms today. Nope. Instead, we're going to get practical. We are going to follow a single, humble data packet on its entire journey, all the way from a user's browser deep into a Kubernetes cluster. By tracking its path, we're going to uncover how this incredibly powerful system actually works, and maybe more importantly, how it deals with things when they inevitably go wrong. So let's just start with the big question, the one that really gets to the heart of it. Your application is running perfectly, handling requests, and then, poof, a pod, which is just the basic building block running your application's code, it just crashes. What happens next? By the end of this, you'll understand the magic behind what makes Kubernetes so famously resilient. All right, let's meet our hero for today, a single data packet. It's just a simple request sent from a user somewhere out on the internet, and its one and only goal is to reach an application running inside our cluster. Its big day is about to begin. First stop, the cluster's front door, the ingress controller. You can think of it like a super efficient receptionist for all the traffic coming in. It takes one look at the packet's destination and knows exactly where to send it. It points the packet towards something called a Kubernetes service. Now that service, this is the really clever part. It provides a single, stable IP address. This means the actual pods doing the work behind it, they can crash, get replaced, get scaled up or down, and the outside world never has to know. That stable virtual IP is an absolutely crucial layer of abstraction. So our packet has arrived at the service's stable virtual IP address. But wait a minute, that's not a real thing. You can't send data to a virtual idea. So how in the world does the cluster translate this abstract address into the actual physical location of a real running container? Well, the answer lies with this unsung hero of the cluster, kubeproxy. This little guy is a network proxy, and it runs on every single machine, every node in the cluster. Its entire job, its whole reason for being, is to watch the services and their pods. And as soon as something changes, it rewrites the actual networking rules on the node itself to make that virtual to real translation happen instantly. So when our packet hits a node, it's kubeproxy's rules that basically say, oh hey, you're looking for this service? I know exactly which pod to send you to right now. And, from a senior engineering perspective, this is where it gets really fun. How kubeproxy does this isn't a one-size-fits-all deal. It's a classic performance trade-off. The default mode, IP tables, it's rock solid, it's been around forever, it works everywhere. But if you start scaling to thousands and thousands of services, that list of rules gets gigantic, and finding the right one can start to slow things down. That's when you can flip the switch to IPVS mode. It uses a much more efficient hash table right inside the kernel, giving you super fast lookups and even smarter load balancing options. This is a real-world decision you have to make. Stick with the old reliable or opt for the high-performance engine for your massive scale cluster. It all comes down to your needs. So, thanks to kubeproxy, the magic trick is complete. That virtual abstract address is gone. Our packet has been given a final, concrete destination, the real IP address of a specific running pod that's ready to handle the request. The connection is just about to be made. Our packet is literally moments away. It's crossed the internet, it's gone through the ingress, it was routed by a service, and its destination was translated by kubeproxy. Everything looks perfect. But in distributed systems, we know we always have to be prepared for failure. And then, the destination pod crashes. It's just gone. So what now? Our packet is flying towards a dead end. And what about all the other packets right behind it? Is the entire application down now? This is where the entire philosophy of Kubernetes just clicks into place. It's all about a constant process called a reconciliation loop. Like the quote says, the controllers are the brain of the whole system, and they are always working, nonstop, to make the real world match the world you told it you wanted. This whole system works because of a declarative model. See, you don't give Kubernetes a to-do list. You don't tell it, hey, go start a pod, then watch it, and if it fails, please restart it. No. Instead, you just declare the final state you want. You write a file that says, I want 3 copies of my application running, always. You just define the what, and you let the Kubernetes control plane figure out the how. So let's see this brain in action. The instant our pod vanished, the actual state of the cluster, which was now 2 running copies, no longer matched the desired state, which was 3. That mismatch is like an alarm bell that triggers an immediate and fully automated response from the control plane. And this isn't just one thing happening, it's like a symphony of different specialized controllers all working together. First, the deployment controller notices a replica is missing and immediately says, we need a new one. Then the Kube scheduler jumps in, looks at all the available nodes, and finds the perfect new home for this replacement pod. The kubelet on that chosen node gets the order and springs into action, starting the new container. As soon as that new pod is up and running, another controller, the endpoint slice controller, sees it and updates the service's list of good destinations. And that action, right there, triggers our friend kubeproxy on every single node to rewrite its networking rules. This whole chain reaction happens automatically, usually in just a few seconds. So what's the end result? The very next packet that arrives at the cluster's front door is just seamlessly routed to the brand new, healthy pod. Our original packet might have gotten lost in the chaos, but the service recovered so fast that from the user's point of view, they probably never even noticed a problem. Maybe they hit refresh and everything just worked. So what can we take away from our little packet's very dramatic journey? Let's quickly recap the powerful ideas that make all of this incredible resilience even possible. When you really look at it, this isn't just a list of cool features. It's a completely different way of thinking about how we manage our applications. Because we use a declarative model, we get this automated reconciliation for free. That makes the whole system self-healing, because it's built with the core assumption that things will break. And it all works so beautifully because the components are decoupled. Each controller has one very specific job, and they all coordinate to create one heck of a robust system. And that leaves us with one final, and I think, pretty big thought. If the platform underneath our code can automatically handle failures, restart containers, and reroute traffic all on its own, what does that change about how we as engineers should be designing and building our applications in the first place? How can we really lean into this resilience to build even better, more reliable software? Now that is something to think about.